Welcome to
ready.
4 years can be a very long time. Mesocosm Study steers Utah Lake Restoration. Our guests today are David Richards with OreoHelix and Theron Miller with Wasatch Front Water Quality Council. We've got 5 minutes set aside for questions at the end.
4 years can be a very long time, and I'm not just talking about our 4-year study, but so we're thinking mesocosm studies can help steer Utah Lake restoration. And we had a bunch of people working on this. You can see everybody that's been working on this. We had multiple progress reports and annual reports, and what I'll be talking about now is our final report. And a lot of these are on our my ResearchGate website. And most of this was funded by the Department of Forestry, Fire, State Lands with little help from Timpanogos Special Service District and the Wasatch Front Water Quality Council. As you guys are all aware that restoring Utah Lake is very important. We're talking about restoration, not enhancement. A lot of people say enhancement, but no, we're talking restoration. So we're talking about algal blooms, ecosystem utilization of nutrients, impaired water quality, loss of native biodiversity, including Bonneville cutthroat trout, which is I'm a proponent of. Let's get the Bonneville cutthroat trout out there at least seasonally, and ecosystem function.
So I'm going to just start with just a little bit of information. So there's probably a large number of you who don't know what the Water Quality Council is, the Wasatch Front Water Quality Council. And so just to explain how we got started, what we do and why we do it. So we're a consortium of special service districts and public works departments from municipalities up and down the Wasatch Front. So what we do is we treat wastewater. That's our primary job, okay? And so part of this, a large part of it is in relation to NPDES or discharge permits. So what happens is nutrients have become a big issue in recent decade or two, and so a large part of our focus is on nutrients in receiving waters, and in this case, it's in Utah Lake, and there's big issues related to why we do that, and one is there's lots of environmental conditions. There's temperature, there's pH, there's redox, there's organic material, and particularly in the sediments of lakes, and these can drastically change or interfere with the reactivity of biota to nutrients based on the speciation or the bioavailability of nitrogen or ammonia or phosphorus. And so a large part of our work has been focused on nutrients. And this variability has been to such a degree that even EPA has not promulgated national nutrient criteria. Most of us know that they've got their priority pollutant list and so forth, and they've set out national standards that we are supposed to meet as states, and this just hasn't been done for nutrients, and it's because of this variability. So what do? They leave it up to the states to develop nutrient criteria, and that's where we're at. And as ecologists and chemists and so forth, this is a difficult task. So no wonder EPA left it. So a lot of states are in kind of a conflict with EPA or a conflict with dischargers on how we establish criteria with which to use to enforce against these criteria for compliance with the standards. So anyway, we got started in this about 17 years ago, and the reason is we want to elucidate what these factors might be. And so anyway, what happened about 6-7 years ago is the state organized a water quality study. They funded it, and they hired a science panel, local and nationwide experts, to work on these issues. Now, we already knew pretty much what the concentrations were of nutrients in Utah Lake. So we're down their list a little bit. We're still working on our criteria, but what will happen is if we can establish our criteria, then we can use this to compare if we have a violation. Now, we all know that we've got an algal bloom problem and so forth, and this has been the primary focus of our studies, is what's adding to or causing these algae blooms. So anyway, I got ahead of myself here. So part of this TMDL, or this assessment process, is developing a nutrient budget. And this is where we've spent an awful lot of time and money, both within the science panel and with the council. So the issue that we've worked on is there's two sources of phosphorus and nitrogen to Utah Lake. And this little pie chart here describes a simplified nutrient budget. There's wastewater treatment. The green is the POTW, the orange is non-point sources. The dark orange is atmospheric deposition, and then the big purple color is sediment recycling, or sediment flux back into the water column. And we've done a lot of research on identifying these other two. Now, these other two, the sediment recycle and atmospheric deposition, there's no guidelines. EPA does not recognize these as primary issues. Here in the West and here in the Salt Lake in Utah, Canada, you know that we're in the basin of what was a huge ancient lake, Lake Bonneville, that went on for many, many millennia. And so sedimentation of the dust, sedimentation of the algae blooms and so forth, it's accumulating in the sediment. And there's a lot of nutrients in this sediment. Okay, that's what led us to looking at this as a possible source of nutrients. And of course, being in this basin, we all know that we're losing our lakes. We're losing Great Salt Lake. We're going to try to stop that. But in the meantime, we have huge areas of playas that also release lots of nutrients and other contaminants that we all have heard of now that can drift with the dust and the windstorms across the basin and even our urban areas. So we're looking at the nutrient component of those, okay? And as we found out with our initial work, that these are extremely large sources. They are the vast majority of the loading of nutrients to Utah Lake. So we started working on this about 6 years ago. We've hired Steve Nelson, who recently retired from BYU, a very talented chemical geologist. He's done some freeze core samples for us, and it's in the middle of publication now. And what he does, it's a stainless steel wedge filled with liquid nitrogen. You drive it into the sediments, and the liquid nitrogen, of course, being about a minus 300, freezes the sediments. What you can do is you can pull that back up, and it maintains the integrity of the sediment profile, the structure. And so with that, you can identify through the strata what the pore water concentrations of nutrients are. And you can see a gradient from the surface down into the sediment layer, about 10 centimeters. So applying Fick's law of diffusion, this is a natural law of nature, Fick's law. You can calculate the loss of nutrients up this concentration or down this concentration gradient into the water column. Mitch Hogshead did another study on this using SOD chambers, sediment oxygen demand chambers. So he simply put these chambers on the bottom of the lake for about 6 hours, and he measured the increase of nutrients, nitrogen and phosphorus, in these chambers. So Nelson calculated 450 tons of phosphorus coming into the water column from sediments, and Hogshead estimated 950 to 1,500 tons. And his is higher because we know that Utah sediments have a lot of organic matter, and those undergo diagenesis, decomposition, and that themselves releases more nutrients off of those very superficial mucky layers than the sediment itself. So that would be a logical addition to the water column. And then also with atmospheric deposition, the picture on the left is a picture of our sampler, just a passive sampler that's on Bird Island. We did that for 2 years, and we measured the fallout from the atmosphere, the dust, the wind, the temperature inversions, the fires, all the things that wonderfully, that are happening in our watershed. And so in this particular case, we have wet and dry deposition that we can sample, and we did that for about 6 years on that. Now the picture on the right is after questions arose with what's in the middle of the lake. In other words, do we have attenuation that falls off as you go across the lake? We put an active volumetric air sampler out in the lake and to measure what is reaching bird island out of the south central part of the lake, okay, as compared to shoreline sites. So here's just one summer's data. So these are samplers on west side, on the east side at Provo High School, Mosida, and at Bird Island. And the point to be taken is if you can look at the blue lines, that's the Bird Island. So really there's not much attenuation. And this sampler collects on the 0.25 micron size. So it's like the air quality samples that you see on TV on the weather every day. What's the quality of our air? All that is particulate matter. So this is measuring the particulate matter as what we breathe every day. So it's the same kind of thing. Here's a revised nutrient budget for the lake. And this is the point that I want to make is that, we measure the POTWs, or wastewater treatment plants, in relation to non-point sources, atmospheric deposition, and sediment recycle. And the one on the upper left is the low end of our variable numbers that we have in atmospheric deposition or sediment recycle. You can see we're at about 16% of the total nutrient load for phosphorus anyway to Utah Lake. Only 16% is from our wastewater treatment plants. In this case, about 78% is from uncontrollable sources of atmospheric deposition and sediment recycle. If we use the high end of our estimates or measurements for AD or sediment recycle, it's an even smaller portion. Then the bottom one is in another year or so at the latest, Provo, Orem, Timpanogos, all these larger plants will finish their upgrades. So they're going to reduce phosphorus from their discharges by another almost 50%. So it'll be only about 75 tons from our wastewater treatment plants. And if you use even the low end of our AD or our sediment recycle, okay, still only 10% of the nutrient load to Utah Lake. So this brings up a question of, are we going to spend more money on our wastewater treatment plants, trying to knock out maybe another 5% at a cost of about $1 billion more dollars? B with a, B for billion? Because they've already spent about $800 million in Utah County on wastewater treatment for nutrient removal. And it hasn't done a thing in 30 years of data from Utah Lake.
All right.
So we're worried about that. So anyway.
Thanks, Theron. Here's just a few of the impairments that our Utah Lake has been facing. The list goes on and on and on. You might be aware of ecosystem shifts, alternative stable states, and hysteresis. Utah Lake has gone through all of those, and we are right about here. So Utah Lake was once clear water, lots of plants growing in it, a lot of mollusks and native fishes, but then it went through this catastrophic ecosystem shift to a lower stable state, and we're here to get back up to the clear water state. It's going to have to go all the way back here, way more than what has caused it, so it's a lot more effort. We're not saying that we can't possibly get even worse and go to an inhospitable Utah Lake. Utah Lake is not quite so bad as some other lakes in the world, but it's still pretty much impaired. So here's our mesocosm. Mesocosms are limnocorrals, and what ecologists do and scientists do is basically we quantify the obvious. So what our limnocorrals did was to block the wind and wave turbation. And as you know, Utah Lake could get pretty windy and it causes turbation. We try to keep the carpet catfish out for the bioturbators, and we try to keep the zooplankton fishes out from the corrals as well. Here's a little diagram of what the corrals are. They were modified and improved each year, sometimes within a year, because Utah Lake, the wave action kind of beat those corrals up, and we had to fix them quite often. The corrals were relocated each year in this area here, right there. So they were moved around a little bit in that area, and they were semi-permeable over and under, so water came over the top, and sometimes came through the bottom. Sometimes fish got washed in, sometimes they got washed out. But we have to remember we looked at seasonal, not long-term effects, so that the corrals were out there from about mid-May till mid-October, so we don't have long-term. These weren't long-term and kept over the winter. We used a lot of, we collected lots and lots of samples for our light attenuation. We looked at Secchi depth and par light meter, had 489 samples of that. Phytoplankton, we collected 367 samples. We did paraphyton samples. We did zooplankton samples, almost 300 zooplankton samples, and benthic invertebrate samples, 145. We use a lot of different statistics, univariates and multivariate community statistics like multiple response permutation procedure and indicator species analysis. And then since we had 4 years of data, we were able to develop mass balanced bioenergetic food web models using EcoPath, which is a really popular model used all over the world for fishery studies. And we created a model for inside the corral versus outside of the corral. And this allowed us to conduct ecosystem network analyses. And we developed more than 34 metrics for these. And some of the results I'll show you in a second. This is a pretty cool image. This is an infrared image of the algal blooms in Utah Lake in one area. So it's pretty cool to look at the infrared images as well. So light attenuation is the big thing. So the corrals block the wave action. And we had higher Secchi disk readings inside the corrals than outside of the corrals. And the light attenuation using the power-based method also showed that we pretty much doubled the amount of light going down to the bottom of the corrals, inside the corrals and outside of the corrals. It's a really interesting measure. It measures micromoles of photons per square meter per second. So that's a pretty cool thing. So the importance of reducing light attenuation is what we want to get Utah Lake is to have light going down to the sediments so we could get plants to grow and benthic algae to grow and reduce the, this profundal zone where no light is reaching the bottom. So that's important of getting light down to the bottom. And that will allow the benthic algae community to grow, the sediment stabilization, including reducing nutrients leaking into the water column, because the benthic algae and the little animals that live down there will prevent sediment coming in. Like Theron said, there's lots of sediment, phosphorus coming into the lake. And we grow macrophytes, aquatic plants, and bivalves, clams, and mussels, and they're going to also help stabilize the sediments. And that's going to reduce what I like to say is improve nutrient utilization. We know the nutrients are a problem in the lake, but I think it's because the nutrients aren't being utilized as efficiently as they could. So we've had positive effects on the phytoplankton, the periphyton, zooplankton, and benthic invertebrates, and you could look at all our reports on the website, or you could find them maybe from the Wasatch Front Water Quality Council. Zooplankton, the biomass of zooplankton was much greater inside than outside of the corrals, and that's pretty important because the zooplankton were grazing on the cyanobacteria. There was less cyanobacteria inside the corrals than outside, more diatoms and green algae inside the corrals. And so the zooplankton responded positively. And of course, there was very few predators and more for the zooplankton to eat these algae. So what we want is more larger zooplankton in Utah Lake when we go to that direction. Multivariate statistical analysis, the dissimilarities between the assemblages, they were all significantly different, the phytoplankton, zooplankton, benthic invertebrates. Indicator species analysis showed that there was more diatom species. There were indicators in there. We have larger zooplankton, the Daphnia were much more abundant inside the corrals and outside. And the benthic invertebrates were more associated with larger sized sediments and less organic matter. And benthic algae, we took our benthic algae samples, and if you extrapolate that over area, you could, by stabilizing the sediments and getting light penetration, you can get almost 50 metric tons per hectare of benthic algae, which is really important thing to do. And the periphyte, inside the periphyte and all this algae, there's invertebrates living in there. And so we extrapolated out that perhaps 24 metric tons per hectare of benthic invertebrates is a lot of fish food that can be grown if we start establishing that benthic assemblage and getting the littoral zone down further extended into the lake. So one of my favorite things is look at food webs. So these are food web flow diagrams inside and outside inside and outside, and biomass based and production based. So you can't really see this, but it's pretty, this is the model that we use to compare inside versus outside. If you guys are really interested in ecosystem networks, this is called the Lindemann spine, and this is from the outside of the corral. So this is detritus, the primary producer, secondary, tertiary food web levels. So it's pretty interesting that people that work with ecosystems use the Lindemann spine quite often. So I wanted to summarize it. To summarize it, Utah Lake has good resistance but low resilience. And resistance is a kind of a double-edged sword. So it's resistant to change in either direction. So it's going to be resistant to improvement, but it has low resilience. So resilience is more of the slope towards recovery. So that's going to be a challenge for Utah Lake. And Utah Lake is kind of trapped in an early successional stage. So that means that the turbation keeps the system from maturing, so it's always getting turned over, that's turbidity, so it's these early successional kind of ecosystem functions. So to summarize the discussion here is that by doing the restoration, we could better utilize the nutrients in Utah Lake. And remember, the corrals were only for a season, so they didn't measure the long-term effects. And they were located by the outflow of Timpanogos Special Service District, so it's one of the more impaired parts of the Utah Lake. So if we could show improvements there, we could show it pretty much anywhere in the lake. And we wanted to use food web models and ecosystem networks analysis. They're extremely beneficial, and they need to be included in any holistic management of Utah Lake. So the goals here would be sediment stabilization, carp reduction, of course, more natural hydrograph, balanced food web, nutrient utilization, restore the native biota, including Bonneville cutthroat trout, and reduce turbidity. And all those will work together, positive feedback loops and synergistically to start improving Utah Lake's condition. So it's a cost-effective way to improve Utah Lake, and it can be a massive income generator. The better Utah Lake is, the more people are going to want to use it, and the more resources will be available for Utah Lake. And as you all know, there's lots of groups now interested in restoration, and they're all doing great work, so they all have to be commended on this. And once again, we quantified the obvious, and that includes the much needed food web and ecosystem function models. So with that, I think we've got 2 minutes extra, all right.
Thank you for your presentation. It was great. The second to last slide where you have the loop going around, about how long do you think it would take to accomplish that cycle, your goals?
Oh, well, they're still working on carp reduction. It kind of slowed down. The carp reduction program kind of slowed down for the last few years. So we got to start getting more reduction in carp. Sediment stabilization, that could take a while, but if you get rid of the carps, there's going to be less sediment problems with the sediment. It could take a while, but we could, as we showed in those, just in one summer, we showed improvements. So it won't take as long, it won't take 10 years. You could start seeing improvements within a year or two. And balancing the food web, of course. So I'm not sure how long it'll take, to tell you the truth.
I was curious, long term, if there is some increased stabilization and more people end up recreating on the lake, do you think that could be a method of increasing turbidity once again if there's more recreation?
From the motorized recreationalists?
Yeah, motorized or just
Oh,
people
yeah.
using the lake in general. I know it's not especially deep, so.
Well, if you ever looked at the Google Earth images of Utah Lake in the summertime, you could see the trails from the motorboats. So once we start getting macrophytes growing and benthic algae growing and reduce the carp, reintroduce the native bivalves to help stabilize that, and then they're going to start working together and increase that. They're going to be positive feedback loops. So increased recreation, who knows? But if the sediments are stable, they're not going to stir it up as much. They might have problems going through those thick macrophytes, the filamentous benthic algae, but at least it's not harmful algal blooms.
I had a comment regarding the treatment plants versus restoration idea. I think to me, in my mind, those are very separate things. So it's kind of, rather than one or the other, it's both, it's and. So the treatment plants, their job is to treat our water and clean our water, and they should focus on that, and that costs money. And then completely separate from that is restoration of the lake. That's done by different people for different reasons and also has a cost, and I think we should be doing both.
Absolutely, we have to be doing both, Theron.
Yeah, so, in most cases, maybe, I don't know. What we've done with atmospheric deposition and sediment recycle is pretty new. There's literature on it because we know it's been going on, and there's literature back in the, 1980s and so forth. But, what we're looking for at least, I mean, if you proceed with nutrient removal through POTWs, you're cutting off a really small slice of that pie for improvement at a very large cost. So even if we started doing some of these things like wave breaks or something like that, that we could clear the water up, that would even enhance predation on the carp, for example, by the predaceous fish out there. So certainly we would favor at least a multi-pronged approach. What we've done now is spend about $800 or $900 million on the plants just for Utah Lake. And if we go down another increment, the next level is just above reverse osmosis. That's going to be another $1 to $1.5 billion to do that. So we're saying is, let's try an alternate route for a tiny fraction of that, even at a stepwise, process, adaptive management process, we could get a lot more bang for the buck. That's what we're proposing to the citizens is let's look at these alternatives before we make that big giant step, for which we can't take a step back when you build those things. They're built and they'll be in place. And then, of course, the issue is water reuse. We'll need water to get to the lake and keep the water in the lake or in Great Salt Lake. So definitely multidimensional issues at play here on what we're trying to do.
How many species of fish are in the lake now?
We go through the list, there's a lot.
Believe it is
And
too.
almost all of them are invasive.
And
And
how
so-
many species were there when the pioneers arrived?
There was almost about half of when the pioneers were here. Bonneville cutthroat trout, Utah Lake, Utah sucker, June sucker, the Weberg sucker, a couple of sculpin species, a bunch of minnow species. So there was not quite as many native species, but it's pretty reasonable. And so they follow different ecological niches. And now all the invasive species, I'm calling them invasive, they were intentionally introduced. So people kind of like those fish, but I prefer the natives. There's lots of those out there, and they're altering the food web. But once again, we'll never get rid of all of those. And so what we have to realize is that we're never going back home. Like, this is not Kansas anymore. We're never going to go back home. So we're going to have to live with what we've got, but we could push towards that direction of getting the best as we can.
Okay, according to the State Museum at Camp Floyd, there were 38. And the question is if you're ever going to get back to anything close to that.
Well, the Utah Lake sculpin is extinct. If it ever existed, it's extinct. So the leather side chub, I think we could get as many of those back as we're willing to try to do. I'd like to see them as many come back as possible.